year. When you come to the final year, you have to give comprehensive viva voce examination, right? For dual degree, they give one in your ninth semester, another in 10th semester. So two comprehensive viva they give. For BTech, only one comprehensive viva, BTech electrical, BTech instrumentation, and dual degree in three different specialization. So for that also I am arranging their board and this thing. So it takes time, right? And your like your final year BTech electrical is 58 student, BTech instrumentation 24 students, and dual degree where your that is fifth your fifth year including BTech and MTech, that is 51 students. So all these things comprehensive IOC I arrange, right? And all the boards, members, faculties, all I have to arrange. It takes time. Different your what you call activities we have. I am also the PG coordinator from my department, right? Our departments, all these things are there. That's why even final year student also design, I didn't reply. I also given them some special thing. I told them, if you can do it this thing this time, I'll see whether everybody has done it or not, then you will get 4 extra marks, but anyway it will not cross the maximum marks of the subject, right? So anyway, they have also done it. So far I have not replied, but I'll reply. Your case also, all I'll reply. I know you have sent me many things, I'll reply, right? And but anyway, come to this thing. But just let me tell you, those who have written your those equations, I have given marks. But if calculations are not shown, final answer is given, I have not given marks. Only 1 mark is given, right? Right. Detailed calculation time was given. Sufficient time was given. And anyway, some of you have make mistake also, like forming y bus matrix. Maybe you have not read anything. That's why it's total complete mistake. Anyway, so let me share the screen and just start this fall studies. But some of you are really good, very good. I have to appreciate that. But anyway, hopefully some of you are in the department, and I mean in the campus. Some of you in the your what you call maybe at home, right? But anyway, when you will be next semester, hopefully all of you will be here. Expecting that nothing will happen now. Now COVID situation is very good, right? And not much, and no new version, nothing is there. It is I mean, even I am also going out without any mask, also keeping mask in my pocket, but I am also going without any mask. Things are okay now, quite normal, right? Anyway, so when you come to the department, at least some of you can meet me in my office. I do not know any one of you, right? So anyway, so thank you very much. So I'll now start. So let me share my screen. Right, all of you have got good marks, but if you want to base grade, you have to do something, like something, right? Anyway, so I'm sharing my screen, right? Uh, so it is visible to all of you, isn't it? Is it visible?
Yes, sir.
These things are very simple. Only one thing you will keep in mind, that zero sequence current for this thing, generally it goes to the ground, right? That should be always in mind. Actually, this way components are broken such that, calculation, fault calculation, everything to some extent will be very easy, right? So now sequence impedance of transmission line. So parameters of if you read it, every step I have written when I was writing the book, every step, but this book was not revised after that, because that publisher, those fellows are not that interested, or this thing, your what you call. But this book is your what you call, that many places it is available in the library and people are following it, because I know it. And your and as far as citation is concerned, I think this book till now has been cited, I think, nearly 150 times, right? So I thought I'll add something on microgrid and other thing, but anyway. So parameters of transmission lines, generally we have seen it in chapter 2 and 3, that is your inductance, capacitance, right? So basically transmission line is a static device. Therefore phase sequence has no effect on the impedance, right? Because currents and voltage encounter the same geometry of the line, because no rotating device, it is a static device. Therefore positive and negative sequence of transmission line same as it is, that is Z1 is equal to say Z2, right? But when you talk about zero sequence current, right, you will find high tension transmission line. If you look at the top of the tower, you will find that your neutral wire has gone on the top of the tower, right? So zero sequence current are in phase because those things, traveling waves, lightning arrestor, all these things cannot be covered in a single power system course. Generally, in many places in NITs or maybe other engineering colleges, there you will find they have 2 3 different parts of your what you call that your power system course. They may have transmission and distribution, generation, all sort of things, right? But here you, as you have varieties of elective subject and several courses, so we have restricted to your what you call only one. Earlier maybe it was power system 1, power system 2, like this. A control system also, it was control system 1, control system 2. Nowadays you are learning only one control system, right? Because of, with the time things are changing, many things are changing, new subject, new thoughts are coming, new, so many new things have been developed, right? So that's why we have made it one. So as mentioned earlier, zero sequence current are in phase. That is at the time of, I told you, positive sequence, negative sequence, zero sequence, all are in phase and flow through the phases, that is your ABC conductors, to return to the grounded neutral, because the zero sequence current will flow to the neutral. The ground or any shielding wire are in the path of zero sequence, and the zero sequence impedance is Z0, which includes the effect of the return path through the ground, that is different from Z1 and Z2, right? So now suppose if you want to get an idea, suppose you consider this your what, this is a simple, just for the purpose of example, this transmission line considered 1 meter length of a three-phase line as shown in this, right? The ground surface is approximated, this is an assumption, the ground surface is approximated to an equivalent fictitious conductor located at the average distance dn. This is given average from the conductor to this, it is dn, right? Very, very rough assumption, right? The phase conductors carry zero sequence current with return path through a grounded neutral, right? So suppose in a b, here this is your a, this is your B, and this is your C. So IA0, IB0, IC0. And distance between any two conductor is D. I mean, no, we didn't consider different distance, that is asymmetrical spacing or the symmetrical, and ground, that is assumed as a fictitious conductor, equivalent fictitious conductor located at a distance dn, right? So if you write that current thing, that IA0 plus IB0 plus IC0 plus IN is equal to 0, right? This way we write that current balance equation. But IA0, IB0, IC0 all are equal. Therefore, we can write IN is equal to minus of 3IA0, right? So this is the common thing. But generally, zero sequence current means it's current flowing to the ground, right? If it is not grounded, no zero sequence current will flow. That we'll see later, right? So now from the equation 2, chapter 2, that is 46, the flux linkage equation, the 2 into 10 to the power minus 7, then you write IA0 ln 1 upon r dash plus IB0 ln 1 upon d plus IC0 ln 1 upon d, because all are d d d, right? Plus IN, that is current flowing to the neutral, but it will be IN ln 1 upon dn, right? So now these are all are same, IA0, IB0, IC0, and IN is equal to this. Therefore, lambda flux linkages will be 2 into the power 10 to the power minus 7 IA0 ln dnq by r dash d square Weber transfer meters, right? Now what you do, this equation, that is your L0 is equal to lambda A0 upon IA0. Therefore, this is 0.2 ln dnq upon r dash d square millihenry per kilometer. Now this equation, numerator and denominator, you multiply by d, right? Not shown here. Directly it is written, you numerator and denominator you multiply by d. So this will be dnq by d cube. Another part will be d upon r dash into dnq upon d cube, right? That thing you can write L0 is equal to 0.2 ln d upon r dash plus your, because of dnq by numerator denominator you are multiplying your d, therefore dnq by d cube, and this dr is here, plus the 3 is out because it is dnq upon dn by d whole cube. So 3 into 0.2 ln dn upon d, that is millihenry per kilometer. Or this is your what you call x0, that is can be written as, this is L0 is equal to, this is L0 is equal to L1 plus 3 Ln, something can be written. So in terms of reactance, you can write x0 is equal to x1, this part is known to you, plus 3 into xn. This is due to your current flowing to the neutral, right? So that means that zero sequence impedance always greater than your what you call that positive sequence, your impedance of the transmission line. Here it is written X only, right? And generally for transmission line, for these kinds of studies, we will neglect R, because otherwise things will become very complicated. I mean, calculation will become very complicated, right? So 3 times the positive or negative sequence impedance. So X0 is equal to X1 plus 3Xn, right? So this is actually, if there is no reactance to the ground, for example, later you will see that, then X0 is equal to X1. Later we will see that. That is called solidly grounded. That means no reactance, right? Now, sequence impedance of synchronous machine. So in this case, what will happen, details are beyond the scope for this course, but in PG level it is there. Generally, that your synchronous machine is designed with symmetrical windings, right? Because 120-degree apart, all the phases, and it induces EMF positive, your induces EMF of positive sequence only. There is no negative sequence voltage for synchronous machine. The positive sequence generated impedance is the value found when positive sequence current flows due to an imposed positive sequence set of voltages. You neglect the armature resistance. The positive sequence impedance of the machine is Z1 will be JXD double dash. That is if subtransient is of interest. Z1 is JXD dash if transient is of interest, and Z1 is equal to JXD if steady state value is of interest, right? So now with the flow of negative sequence current in the stator, the net flux in the air gap rotates an opposite direction to that of the rotor, because positive sequence is clockwise. If it is, the negative sequence will be anti-clockwise. Therefore, relative speed will be the net flux rotates twice the synchronous speed of the rotor, right? But in the case of in this case, field winding has no influence, because field voltage is associated with the positive sequence variables. If you see the geometric structure of, I mean, next class I'll show you. Today I didn't make it ready. I'll show you how this geometrical structure, right, and how coupling comes also. But in your case, no coupling is there. I have a beautiful notes on that. Next class I'll show you, right? In this case, field winding has no influence, because field voltage generally is associated with the positive sequence variables, and only the damper winding produces an effect in the quadrature axis. Therefore, the negative sequence impedance is very close to the positive sequence subtransient impedance. That is Z2 is approximately JXD dash, right? Because it is in your what you call, that is in quadrature, right? So it should be JXD double dash, right? So I don't know, machines, maybe in synchronous machine they might have taught it, but in PG, that how things are happening in PG courses. Particularly, we have a course, power system dynamics control, right, monitoring. The whole dynamics means basically it's a synchronous machine dynamics, right? Anyway, so Z2 is approximately, you can remember, the JXD double dash, right? So this is actually, and for leakage reactance, this is for negative sequence. And for leakage reactance, if synchronous zero sequence, right? If synchronous machine, the no zero sequence voltage is induced, right? Only positive, whatever synchronous machine voltage is there, that is basically positive sequence voltage. Zero sequence, negative sequence, no negative sequence voltage for synchronous machine. Similarly for zero sequence. So zero sequence impedance of the machine is due to flow of zero sequence current, right? The flow of zero sequence current creates 3 MMFs, which are in time phase but are distributed in space by 120-degree, right? Therefore, resultant air gap flux would be 0. Hence, there is no reactance due to armature reaction. Therefore, the machine offers a very small reactance due to leakage flux. Therefore, the rotor windings present leakage reactance only to the flow of zero sequence current, that is Z0 is equal to JXL. XL is the leakage reactance, right? This is how Z1, this is how Z1 positive sequence, this is for negative sequence, and this is for zero sequence, right? As far as as far as that machine is not loaded. Now, for synchronous sequencing networks of a loaded synchronous machine, now you consider a three-phase machine. This is in phase A, EA, EB, EC. 3 voltages are there. This is this is your synchronous reactance, ZS, 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 and a neutral is there. Neutral is the neutral connection, and this is your Zn, right? And it is grounded. Now, voltage, if you see that this is VA, that is VAN, that is phase voltage. This is VBN, and this is VCN. And this current going out of the machine, so it is IA, IB, IC, and neutral current is entering. So basically, IN is equal to IA plus IB plus IC, right? We are applying KCL at this point. Now EA is equal to EA, EB is equal to now beta into A, same as before, that 120-degree phase shift, and EC is equal to beta square EA. This way you first make it. So EA is a reference phasor, therefore EB is beta EA and EC is beta square EA. Therefore you can write EA EB EC is equal to 1 beta beta square EA. Instead of writing angle 120 degree or angle minus 120 degree minus 240, or my angle 240 or angle 120, right? Earlier we have seen that your beta, all the property of beta is equal to the power j 120 degree. So accordingly you can write EABC is equal to 1 beta beta square EA, right? Now if you look into this equation, right, you just take one phase, you just apply KVL. For example, this path, this path, this path, this path, and this path. So if you write, then Zs into IA and plus terminal you are encountering first, plus VA plus Zn into In minus EA is equal to 0. Right, I need not write it, right? It is understandable. Just apply in this mesh, apply in this mesh KVL. It will be Zs into IA, then encountering plus terminal first, so plus VA, then plus Zn into In, then minus it coming here, minus EA is equal to 0. Right. Therefore, this VA is equal to, I mean, after that you can write VA is equal to EA minus Zs IA minus Zn In. Similarly, VB is equal to EB minus Zs IB minus Zn In. Similarly, VC is equal to EC minus Zs IC minus Zn In. Right. This way you write this equation for all the three phase voltages. Right. Now you know that In is equal to, from this equation, In is equal to IA plus IB plus IC. Right. This you know. So what you do, this In is equal to IA plus IB plus IC, you just substitute here and simplify. You just put here In is equal to IA plus IB plus IC, here also IA plus IB plus IC, here also IA plus IB plus IC, right? Therefore, VA, VB, VC is equal to this one, and upper simplification, you can write this minus, this is the matrix, into IA, IB, IC, right? Because you have substituted In is equal to IB plus IC. Or in compact form, you can write that your VP is equal to EP minus ZP IP. VP is equal to VA, VB, VC, right, transpose. IP is equal to your IA, IB, IC transpose, and EP is equal to EA, EB, EC transpose. P stands for phase, right? And ZP is equal to this matrix, 3 into 3 matrix, right? Now, if you go to equation 12, you know that VP is equal to AVS. This we have done previously. Similarly, EP is equal to then A into S, same thing. And IP is equal to A into IS, right? If you go to equation 12, you will get all these things, right? Now what you can do is that your VS is equal to positive sequence voltage VA1, VA2, VA0 transpose. ES is equal to EA1, EA2, EA0 transpose, right? As S is equal, IS is equal to that symmetrical component IA1, IA2, IA0 transpose, right? So this already we have seen before. And A is equal to this matrix is also known 1, 1, 1, beta square beta 1, and beta beta square 1, right? Therefore, this equation, whereas a VP is equal to this equation 45, VP is equal to substitute AVS, right? Then EP is equal to substitute AES, and this one, your minus ZP, IP is equal to substitute AIS. So you substitute IP is equal to AIS, right? Multiply both sides by A inverse. If you multiply both sides by A inverse, this will be VS is equal to ES minus A inverse ZP A into IS, right? Or you can write this equation 50, you can write VS is equal to ES minus ZS IS, where ZS is equal to A inverse ZP into A, right? Therefore, ZS is equal to A inverse, we know this one, ZP we know this one, and A is equal to this one. This is A inverse, we have got it before, we know this. You need to multiply, right, and simplify. If you multiply and simplify, finally ZS will become 1/3, then 3ZS 0, 0, 0, 3ZS 0, 0, 0, 0, 3 into ZS plus 3ZN, right? Or this 1/3 is there, you divide it, so ZS will be ZS 0, 0, 0 ZS 0, 0, 0 ZS plus 3ZN, right? Ultimately it will come like this. So this is your ZS. Therefore, you can write that VA, or what you call that VA1, VA2, VA0 is equal to EA1, EA2, EA0. Now putting symmetrical component minus this one into IA1, IA2, IA0, right? This is your what you call, this is Vs is equal to Es minus Zs. So we are putting symmetrical component thing, right? So therefore Ea1 is equal to Ea, Ea2, Ea0 for 0. For synchronous machine, only positive sequence voltage is there, but negative sequence and zero sequence there is no voltage, so it is 0 0, right? Therefore Va1, Va2, Va0 is equal to Ea1 is equal to Ea. So this is Ea 0 0 minus this one, that Ia1, Ia2, Ia0. Therefore Va1 will be Ea minus Z1 I1, Va2 will be minus Z2 I2, and Va0 will be minus Z0 I0. Now where Z1 is equal to Z0, right? Z2 is equal to Zs rather. Z1 is equal to Zs. Here now printing problem, right? It is a little bit this thing. Z2 is equal to Zs and Z0 is equal to Zs plus 3Zn, right? Now if you, now this is using this one you can draw one circuit. Using this one also you can draw a circuit with respect to reference. You have to consider one reference, and with this one also you can do another circuit. So these three equations are independent to each other. These three equations are independent to each other. Now if you do, write your this is a reference, this is also reference, this is also reference. For positive sequence diagram, this is this one. I mean from this equation, this is positive sequence network, right? This is with respect to one reference you have to consider. This is negative sequence network, and this is zero sequence network. These three networks are independent, and this voltage is V1, Va1, right? Then this voltage is your Ea. This voltage is Ea, right? So in synchronous machine, there will be no voltage source for zero negative sequence or zero sequence, and whatever voltage source positive sequence, nothing but is generated voltage, that is Ea. Right. So from the above derivation, following observations can be made. The three sequence network are independent. This is no link to each other. Right. The neutral of the system is the reference for positive and negative sequence network, but ground is the reference for the zero sequence network. Right. And third one is there is no voltage source in the negative or zero sequence network. Only the positive sequence network has a voltage source. The grounding impedance is reflected in zero sequence network 3Zn. That is here. The grounding that Z0 is equal to Zs plus 3Zn. If sometimes we call it is solidly grounded, that means Zn at that time Zn is equal to 0. Otherwise Zs plus 3Zn, right? So that is your zero sequence impedance. And this is for synchronous machine. See, things very easy. Later you will know how, when you will do the problem. At that time, it is open book. Everything will be there. Later at this at that time, I will see how you can manage it. Right? If one can mistake it, then if anybody takes from him or her, then the whole thing will be mistake. Right? So one has to be very careful. Now this is for synchronous machine. Next is for transformer. Transformer is, everything is easy. Only thing is that a transformer is a static device, right? Only our interest will be zero sequence network. That is the most interesting thing for transformer, right? The core losses and the magnetizing current are in the order of 1% of rated value, and magnetizing branch is neglected, right? Because we will consider for the fall studies, so better not to consider the magnetizing current or anything, right? So only thing is that look at that transformer, right? So four connections are there. Whatever is written, everything is written here. Whatever is written here. I will know, you read whatever is written, but just listen what I am telling. This is transformer. This transformer is a star connection. Both side is grounded, right? Therefore, there will be a path for zero sequence current to flow. That's why this is a ground reference, and this is your what you call zero sequence reactance, right? Later will be discussed through numericals what is zero sequence, this thing, right? But this is actually, this side is A, this part is A, this part is A dash. So only this part is drawn A to A dash, and this is through the zero sequence reactance or impedance, right? So this path is closed because this is grounded, this is grounded. So there is a possibility that current flow through the ground. So this path is complete, right? This is that ground reference zero sequence diagram when star grounded. Now second one is that primary side says star is grounded, secondary side no ground, right? Therefore, although it is grounded, and this is not grounded, that means there is no possibility of the zero current, zero sequence current to flow. That's why up to this it is there. After that is open. This you have to show open. Then only you can show that it is not grounded, and that means no zero sequence current will flow. When you tell false studies, this thing you will know the significance, right? Right now, just see this. So this is your star grounded, and that another one is star grounded, and this is ungrounded, right? So this is open, no zero sequence path to flow. Now this one is star ungrounded, right? And your delta connection is there. In delta, there is no question of no question of ground. So in delta, the zero sequence current will circulate inside the delta, but it will not go out, right? And star is ungrounded, so there is no zero sequence current flow. So it will be like this should be open. It is like this one. It is like this one because it is ungrounded. So no zero sequence current will flow, and this is also your what you call delta. Delta actually zero sequence current can circulate inside this delta winding, but it will not go out because no neutral, right? So in that case, you have to show that this is open, right? And another thing is this side is star is grounded, but delta here, the zero sequence current will flow inside the delta, right? So no current will go out. So this is star grounded. So in that case, it connect it. This shows the star is grounded, but your star is grounded, but this is delta. The circulating current will be there. That is zero sequence circulate current inside the delta. It will not go out, but there is a possibility the star delta transformer, that current will from the star connection, it will go to the ground, right? This is reference, right? And third one is that your last one is fifth one, delta delta. Delta delta means that zero sequence current will circulate only inside the delta. So this side you should keep open, this side you should keep open, and you make this connection. This will not affect during the false calculation studies. Later you will show. This side is open, this side is open, so you cannot connect anything here, right? It will circulate inside that, and this is that your zero sequence network diagram for delta delta transformer. This is you have to your what you call this thing when false studies will come. At that time, this thing will be interesting. So all these things, 1, 2, 3, 4, 5, whatever is written here, everything is written here. You just go through it, right? You just go through it, and this is how the zero sequence network for transformer. Actually, it is open book now, and everything you can see. But in general, when your classroom you are writing exam, this is a challenging task for many students for fall studies, right? It is actually anyway. So in our electrical engineering, that your what you call that many such things, many interesting things are there, right? And for easy calculation, and generally in electrical engineering, except false studies, other calculations wherever it is necessary, you use Y matrix, right? But whereas for false studies, it is Z matrix we use due to computational efficiency, right? And nowadays, commercially, many packages are available. Still, many things may not be available, and many software packages may be available. But properly, but when you bring out software thing, one has to be tested very, very, I mean, very carefully that this thing. Suppose for some fault, something. Suppose within 3-4 seconds you are finding very good result, but you simulate the same thing for 10, 15, 20 seconds, whether you see that everything is correct or not. Maybe after some time you can find again something is rising, means that software is not correct, right? So one has to check many things, I mean many things, right? And that's why I mean all side one has to check. Now consider this one, right? This is from your first year magnetic circuit, or little bit you have studied, but this is a simple thing like a three-phase. Just try to understand. A three-phase balanced star-connected load with self and mutual inductance elements is shown. That load, that grounded, your neutral is grounded with Zn to 0, right? I mean, no your grounding impedance. Determine the sequence impedances, right? So this is ZS, ZS, ZS. Current is flowing IA, IB, IC. Voltage VA, VB, VC is shown. This is neutral, right? It is grounded, but no Zn is here, and their mutual coupling is there. There is A to B Zm, B to C Zm, and your A to C Zm, right? All couplings are there, right? And you have to write down the your what you call that that your what you call that sequence impedances, right? So line to line your the line ground voltages are line to ground. VA is equal to ZS IA will be there, but due to mutual coupling, it will be Zm into IB plus Zm IC will come. Similarly, VB also Zm IA plus ZS IB plus ZM IC. VC also ZM IA plus ZM IB plus ZS. If mutual is if there is no mutual impedance, mutual coupling, then only your VA will be your ZSIA, VB will be ZSIB, VC will be ZSIC. But mutual coupling is there, right? Mutual coupling means mutual inductance as the your reactance, but we are representing it by ZM, right? Therefore, VA, VB, BC, you put them in matrix form, it will be like this. Or VP is equal to the phase component, that is ZABC, we have made it because it is three-phase impedance, mutual coupling is there, into IP. VP is equal to this much, VA, VB, BC transpose, IP is equal to like this, and this is your ZABC. Now we know VP is equal to AVS, IP is equal to AAS. This you have seen it before. Therefore, you put it like this, and then multiply both sides by A inverse. Then VS should be A inverse ZABC into delta into IS, right? Therefore, VA is equal to VS is equal to symmetrical component, VA1, VA2, VA0, 1/3. This is your A inverse, then your ZABC, then it is your A matrix into this one. If you multiply these three and simplify, you will find VA1. This is directly it is given, but you have to do it little bit, right? Directly it is given, and VA1, VA2, VA0 will be ZS minus ZM 0 0 0, ZS minus ZM 0, and 0 0 ZS plus 2 ZM, and IA1, IA2, IA0, right? However, Z1 is equal to ZS minus ZM, and Z2 is equal to ZS minus ZM, and Z0 is equal to ZS plus 2 ZM, right? So if it is not there, now one exercise I am giving you, you connect one Zn. Here Zn is 0, here Zn is 0, but Zn not 0. You connect one Zn and repeat the thing and see what difference you can see in this diagram, particularly in this matrix, particularly that 0 sequence one, right? This is an exercise for you. By chance, if it is there in exam, you have to do it, right? So this is an exercise for you, right? So if you connect Zn, right? So next one, start delta, right? First it is delta. This is very simple thing because you have studied in your very first semester, right? Or second semester, because sometimes some are doing physics, chemistry, other thing, physics, ET, and this thing, another semester. Anyway, first year you have studied. This is a simple thing, right? Say suppose it is a delta connected load is there. It is 3R, 3R, 3R. All are resistive, right? So a delta connected resistive load is connected across an power system. Will take later, right? Delta connected resistive load is connected across unbalanced three-phase supply, right? Find the symmetrical component of line currents and also find the symmetrical components of delta current. Both you have to find out. Line current and symmetrical, also find the symmetrical components of delta current, right? All these arrows is given, and A, B, C, that is you know current here IA, IB. So IC you can easily compute. IC is IA plus IB plus IC is equal to 0. From there you can compute, right? Now this is 3R, 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 because when you convert it to star, so division will be easier. That's why 3R, 3R is taken, right? Now if you look into that, IA plus IB plus IC is equal to 0. IA is given, IB is given. So find out IC. IC will be 18 angle 154 degree ampere, right? Now go to equation 24, 25 and 26. There you know expression of IA1, IB1 and IC1. IA1 is 1/3 IA plus beta IB plus beta square IC. Now if you simplify, after substituting all, you will get I1 is equal to 4.64 angle 8.5 degree ampere. Similarly, IA2, if you go to equation 25, 1/3 IA plus beta square IB plus beta IC. Substitute all, then you will get IA2 will be 13.96 angle minus 77.9 degree ampere. Similarly, IA0 is 1/3 IA plus IB plus IC is equal to 0 because IA plus IB plus IC is 0, right? Therefore, IA0 is equal to 0. Now, IB1 is equal to beta square I1 according to that our notation phasor diagram, right? So this is IB1 and this is your IB2, only angle changing, right? IC0, IA0, IB0 all are 0, and IC1 is equal to beta IA1, so this much, and IC2 is equal to beta square IA2, and IC0 is equal to IA0 is equal to 0 ampere, right? Now for checking, cross checking, IA is equal to IA1 plus IA2 plus IA0. Whether it is coming or not, it is coming 15 angle minus 60 degree, right? This is for cross checking. Just one checking I have given, that this is for cross checking, right? So only thing is that computation is little bit this thing because complex quantity is involved. Now converting delta to star. If you convert this delta to star, right? So 3r into 3r divided by 9r, right? So basically it will be r 9 by 9, 9r square by 9, 9r, right? So if you convert to delta to star, it is r r r. This is IA, IB, and IC, right? Now, if you convert to delta, that VAB is equal to RIA minus IB. Here you apply KVL, right? Suppose this polarity is plus and this is minus. So IA into R minus IB into R minus VAB is equal to 0. They are right. So VAB is equal to R into IA minus IB. This you know, I need not write. Huh? This is first year thing. And I actually first year when I used to teach, I taught several times. I used to tell everything in the class, right? How to measure power, how to what meter is connected, like how things will be done, right? Whatever you things used to then some start some your current to voltage to current source transformation, right? Then something your voltage source, current source mix problem is there. If something is there, how to find out the power, some tricky problem was there with me. At that time I used to tell them that this way you should do that. Magnetic circuit also, some thumb rule, which I am not sure whether it was given in the book or not, but somehow I have created from just to remember all these things. I used to tell that how to take the polarities of coupling thing, plus plus plus, plus minus minus, minus plus plus, minus minus plus, right? The way we multiply in mathematics, that way something is there. It is there in my NPTEL courses in fundamentals of electrical engineering, right? There also I have mentioned that how to remember this, right? First understanding, then try to remember. And similarly, IAB is equal to V. If you look into this circuit, if you look, this is AB. So this current, this point is A, huh? This point is B, this point is C. So IAB will be VAB upon 3R. From here, A to B current, IAB is equal to VAB upon 3R, right? So that's why we written IAB is equal to VAB upon 3R. But here from this circuit, we have got VAB is equal to R into IA minus IB, right? Therefore, it is R into IA minus IB upon 3R, that is 1/3 IA minus IB. So no need for if it is given, no need for voltage source to know, right? Nothing is required actually. So that's why this problem is taken. No question of need your voltage, line to line voltage or phase voltage, nothing is required, right? So you know IAIB, right? So IAB you can get it. Similarly, your this is your whatever it comes, right? And similarly IBC will get it same way, IB minus IC. Here it is IAB means your IAB means 1/3 IA minus IB, right? Similarly IBC means 1/3 IB minus IC, right? So this is your IBC, this value 8.33 angle, this one. Similarly IC is 1/3 IC minus IA. So this much. Now same philosophy will apply. IAB1 is 1/3 IAB beta IBC plus beta square IC. Same philosophy will apply, right? So you will get IAB1, that direct positive sequence component of the phase current in delta, right? And similarly your IAB2 you will get like this, and IAB0 also you will get like this, right? This is phase current to delta. Now also note that IAB1 is equal to IA1 upon root 3 angle 30 degree. You can verify. You can verify, right? Similarly, IAB2 will be IA2 angle minus 30 degree. If you can recall this one also, no problem, but you can verify. And IAB2 is equal to, you check, it is your 8.06 angle, this one, right? So this is a simple problem where voltage source is not required, but how to compute line current, and this is required later in power system studies, right? That's why these are the simple problem I have taken, right? So this is one. And another one is that this is actually a balanced delta connected load was there, the three-piece system, and it was current was 15 ampere, right? All of a sudden in one phase the fuse was blown up, right? So fuse melt actually, right? So this is disconnected. Sorry. So so this IA and IC, right? IA and IC, your what you call that your current will be there, but here IB is equal to 0. So if you look into this, then IA will become minus IC, because no current is flowing through this. This IC is current flowing here, and it is entering here, right? So basically IA is equal to minus IC and IB is equal to 0. Therefore, IA is equal to given 15 angle 0, and therefore IA is equal to minus IC. This you take as a reference. Therefore, IC will be 15 angle 180 degree. So minus 15, right? Therefore, IA1 is equal to same philosophy. This formula you put. So this will get IA1. IA2 will be same thing. You will get this one. And IA0 in any way 1/3 IA plus IB plus IC. So this is 0, right? So this is your what you call that your symmetrical component, how to make it, right? Now my question is, here suppose star connection is there, if it is not open, suppose one of the delta part is open, so you find out what will be the positive, negative and zero sequence component of the line current as well as phase current, right? Suppose this is closed, but either of these, suppose one is open, right? Suppose either this or this or this, one is open, right? So you have to find out what will be your this thing, positive, negative, zero sequence component of the line current and phase current, right? So this is a simple problem. Let me see this one. Just hold on. So here, till time is there, it is 10:47 to my computer. So in any way, so suppose this problem. First thing is, this kind of problem, first you look, first thing is that per unit system, although it will not be there in exam, but it has to be there, because everywhere you have to convert it to the all the parameters to a common base. So per unit system cannot leave you, right? See, a generator is there, generator is star grounded. Then a transformer is there, step up transformer. This side is delta, this side is star grounded, right? And then transmission line is coming, E to F transmission line, then T2. This side also star grounded, this side is delta, right? After this to this bus bar, that one generator is there. Your what you call two motors are there. Actually, these are motors. One motor is star connected under your ungrounded, and another motor is your grounded, right? Star connection. So this is given, but because here positive and zero sequence diagram is easy, but negative sequence is a problem, because you have to think this generator is grounded, this is delta star grounded, this side also star grounded, so this side is star grounded, this side is star grounded, so it will get a closed path for zero sequence. But here star is grounded, right? But this side is delta, so it will remain open, right? One has to be very careful. And this is star grounded delta side, this side also path will remain open for zero sequence, right? But before that, you have to make it. This problem is 6, 7, 8 lines, right? First, you have to read carefully. A 50 MVA, 11 kV synchronous generator, that means this one has a subtransient reactance of 20%, that is 0.2 per unit. The generator supplies two motors. This is motor 1 and motor 2 over a transmission line with transformer at both ends as shown in figure 9. This is transformer, this is transformer. The motors have rated inputs of 30 and 50 MVA. This is 30 MVA, this is 15 MVA. Both 10 kV. Terminal voltage is 10 kV. They are rated with 25% subtransient reactor. This is 0.25, this is also 0.25 per unit. The three-phase transformer are both 60 MVA. These two transformers are 60 MVA and they are 10.8 by 128 kV, right? This side is 10.8, this is 128 kV, 21 kV, the line is 121 kV, and this side is 10 kV. But generator motor terminal voltage is 10 kV, so but you have to make it a common base with leakage reactance of 10% is the 0.1, 0.1, right? Now, assuming zero sequence reactance for the generator and motor is 6%, generator is that is this side is the zero sequence is 0.6, for this motor also 0. This is grounded 0.06. Current limiting reactors of 2.5 ohm each are connected in the neutral of the generator of motor number 2. That we will see later. Here it is there. Look, one inductor is shown. This is nothing but a reactor. You need not bother about this. You have to consider the resistance as 2.5 ohm, right? And the zero sequence reactance of the transmission line is 300 ohm. This transmission line, it is given in ohmic value The series reactance of the line is 100 ohm. Zero sequence reactance of the transmission line is given 300 ohm, but the series reactance of the line is 100 ohm. Right? Draw the positive, negative, and zero sequence network. Now, first what you have to do is you have to assume base power say 15 MVA, 50 MVA, and base voltage 11 kV, like your generator thing. Based on that, you convert all the thing to this common base, right? Therefore, base voltage for transmission line will be 11 into 120 on upon 10.8. So 123.2 kV. In proportion to that, you have to change the your what you call this voltage, because transmission line voltage is your what you call 121 kV, and this transformer is 10.8 kV. Why 121 kV? That's why the base voltage of the transmission line is 11 into this one, 123.2 kV. Motor base voltage also, so line base voltage is this. So motor base voltage will be 123.2 into 10.8 upon 1, so 11 kV again. Right, because line is from here to here it is going. Its base voltage is 123 point, your how much you have got? 2 kV. Right, so this side is 11 kV. The transformer reactance is given that this is old value to new base. You go to that formula, right? Per unit system you have to go back again. It will be 0.1, then 50 upon 60 MVA into 10.8 upon 11 whole square. So this much of per unit. Line resistance, positive and negative sequence, right? It is your 100 ohm given, base impedance is kV square upon MVA, so MVA has gone up, right? So 0.33 per unit. Line reactance 0, it is same thing, but again kV square MVA, so it is 0.99 per unit, right? Reactance of motor 1, positive sequence, right? Base voltage for the motor side is 10 kV, but your base voltage is 11 kV, rated voltage is 10 kV. So convert the old one to new one, go to the, again that your formula for per unit system. So 0.25 into 50 upon 30, because that base is for motor is 30 MVA, but your base is 50 MVA into 10 by 11 square. So this one. Similarly, zero sequence reactance for motor, same thing, but 50 upon 30, same thing. Whatever it comes, 0.082. Zero reactance of motor, same thing, but it was 0.25, so it will become 0.69. Zero sequence reactance of motor, same thing. It will be everything. The only thing is that its base MVA is 15. Here it is base MVA is 15. Sorry, 50, and its rated MVA is 15. Rated MVA is 15. Right. And reactance of the reactor, it is base is 50 MVA and 11 kV, so 2.5 into your kV square upon MVA, so MVA has gone up, so this much, right? Once you make it, now it is so reference line you have to draw. Look, and all when you do such thing, then all these things you have to mark. D to E transformer, E to F transmission line, F to G again a transformer, right? G to P one motor, G to Q another motor. These two motors are in parallel. Right? These two motors are in parallel. And subtransient they have asked. It has been asked. So this is a reference bus. This is the EG double dash. You take. Probability you mark. Then this is generator 1, then D to E transformer 1, E to F transmission line, F to G again transformer 1, and these two motor reactants after whatever you have got it and connect it to the reference. This is positive sequence network. Now zero sequence, only when parameter is changed, you will change. Reference, no voltage source. It is same, it is also same, it is also same, it is also same, this is also same, this is also same, but no voltage source. So this is your zero sequence. Sorry, negative sequence. Right. And for the case of zero sequence, this is interesting. This is reference bus. This side is whatever you have got, you connect. But as look at this diagram, this is star grounded and this is delta. So here delta through this delta means zero sequence current will circulate inside the delta. It cannot go to the line. That's why zero sequence, it is your what you call these two zero sequence thing are there. After that it is open. It is kept open. Right. Now this side you see, from this side star it is grounded, this side star is grounded. Whatever transformer zero sequence is there, it will come along with this line, it will come and it will close the path. Right. If you look into this, that this is coming, this is transformer, this is line, this is transformer, path is closed. Right. Now if you come to this one, if you come to this is delta. Right. This side is star ungrounded, so it will not, it will, as it is ungrounded, it is also delta, it will not connect to the reference. sorry, if you see that it is not connected to the reference, but other one, as it is grounded, it is connected. The other one, if you see this is grounded, but this is delta. So if you look into this, then it is your what you call, it is connected to the your this thing reference bus, right? But this one, as it is delta, it is completely isolated. If you look into this, that this side is delta, this is completely, this is the whole thing is isolated from this one, right? Because this is delta, this is ungrounded, so this is not connected to the reference bus. Although it is connected to the reference bus, but overall thing is totally disconnected, right? If you look into this, this one, this is also not for transformer one, ungrounded one, and this is also disconnected. So positive sequence, negative sequence, and zero sequence. Positive sequence and negative sequence quite easy. Zero sequence will problem. If I twist it this way and that way, that will definitely experience in the exam. Later we'll discuss on Wednesday morning we'll discuss right many things and this thing and at that time topic sharing right. At that time you'll be knowing that how things are right. Anyway, try to do well. All of you are getting good marks right. Maximum, but some of you are exceptional. I can make out at least 4 or 5. I have seen very good handwriting, and I believe that all of you may be doing very well in all of you are very good, right? And but some cases I let tell you one thing. Please do all the steps, otherwise I cannot give full marks. Like some of you have done it full, and this time was given sufficient time, 1.5 hours, right? And sufficient things are given, and some of you have done very well. Anyway, after that, the assignment, everything, if you want marks, I can give the marks, but I don't after third tendency. Right. So thank you very much. Again, Wednesday morning we'll meet. Thank you. So I'm leaving now. I have to also go to hospital after some time. Right. So thank you very much. Thank you. Any question? No question. Anyway, thank you very much. I'm leaving. Okay.